The other example of a simple harmonic oscillator is a pendulum. And we're going to look first at the simple pendulum. Now, a simple pendulum is one where the mass is located at the end of a string. So the mass would be here. This would be our string. It would attach to what we call a pivot point or point of rotation. And the important thing about this string is that it is massless and stretchless, meaning that the mass of the string is so small compared to the mass of the object at the end of the pendulum that we can consider the mass of the string to be negligible. That means it does not matter. We also assume that the string cannot stretch, that the length of the string is the length that it's always going to be. And since a pendulum moves in an arc shape, it moves back and forth, it makes almost like a semicircle, we can consider the length of this string to be the radius of our circle. Now, the force that's going to cause a simple pendulum to start moving is typically going to be gravity. So if you pull back an object and then release it, gravity is what's going to make it swing back and forth. So I'm going ahead and drawing a force diagram. Remember, we always draw our labels, our force due to gravity, straight down from the center of mass. We label it, and we put what causes that force in parentheses. There's also a tension force because a string is involved. And so I have my force of tension. I actually mislabeled it, so let's fix that right now. So the thing that causes that tension force is the string itself. So we now have our free body diagram. And once we have a free body diagram, that's when we can go ahead and start writing our Newton's law equations. But if I go to write my Newton's second law equations, I'm going to run into a quick problem. Remember, our F equals ma equation only works in one direction of motion at a time, but we have gravity in one direction and our tension force at an angle. That means we need to break our force of gravity into components. And this angle you see in here will match the angle that you pull the string back, that's created when you pull the string back to release the pendulum. So this angle here is identical to this angle here due to the geometry of the situation. So when we break our forces into components, you end up with mg cosine being lined up with tension and mg sine being perpendicular to that tension force. And remember, I put the components in blue because we never draw them on a force diagram. On the AP exam, do not draw a free body diagram with components included. You will lose points because those forces aren't really there. They're pieces of that red FG force that is acting on the object at its center of mass. So just like we did when we had forces on an incline, I have rotated my axes so that my y-axis lines up with tension and a component of the gravitational force. My x-axis lines up with the other component of the gravitational force. And we see quickly that it's the x component of the force of gravity that's going to cause the pendulum to start swinging, in this case downward to the left in an arc, in a clockwise circular motion if you're going with the shape of a clock. So if I write out my F equals ma equation based on my free body diagram, I end up with this relationship here, that the acceleration of my pendulum in that arc, my linear tangential acceleration, is going to be related to the acceleration due to gravity on that planet times the sine of the angle that you pulled that string back at to release the pendulum. My tension and my force due to gravity in the y are also going to be related to each other. Now, the pendulum is not moving up and down the string this way, which is why there is no acceleration in the y direction. So my tension force is going to equal mg cosine theta. Now, just like with our spring mass oscillators, these forces are dependent upon the angle that's in existence. So as that pendulum swings through its displacement back to being vertically straight up and down, swinging up to the other side, that angle is going to change, which means that our acceleration will vary, as will our tension force, just like it did when we talked about circular motion and how tension would be greater at the bottom of a swing than at the top of a vertical circle due to that pull from gravity either being towards the center or away from the center to maintain a set speed. Unlike uniform circular motion though, our pendulum is going to vary in velocity as it moves from its initial position through equilibrium, up on the other side, back to equilibrium, and so forth. As the pendulum is technically rotating, we can actually say that that force due to gravity in the x direction, that mg sine theta, that force is actually creating a torque causing the pendulum to rotate, because our radius, our string length, is perpendicular to this component of the force of gravity. So that's why we have a sine theta here. Our force would be mg, and r would be our length of our string. Now, if you recall, there are two ways to calculate torque. We can calculate torque as force times the displacement, or distance away from the pivot point, times the sine of the angle between them. Or we can use Newton's second law for rotation and say that torque is equal to I alpha. And the reason why I'm bringing this relationship in is this is what's going to create what we call a differential equation that will allow us to determine the period of any simple pendulum, the time it takes to complete one full swing. So if I go ahead and replace some values, now this negative sign is just here to indicate that it is moving downward at the time, and I've replaced R with L, the length of the string. Now remember, the moment of inertia for something would be given in this case, since we have what we consider to be a point mass, a mass concentrated in a small space. We can calculate that as mass times the radius squared. Again, the radius is the length of the string. And then alpha is our angular acceleration, how quickly this pendulum is going to rotate back and forth in its arc. Now, looking at both sides, I can now cancel some things out. I've got a mass on both sides, and one of these L's, lengths of the string, is going to cancel. You can see I'm left with this acceleration function that I had on the previous slide is equal to a radius times an angular thing. This is what we've been learning about. This is a connection to rotation. So right there, this rotation, or this relationship right here, is just a linear acceleration is equal to an angular acceleration times the radius. Catch to this relationship here. This holds if the angle is small, and I'm talking like 10 degrees of displacement from the vertical or less. Then we can say for small angles that basically the sine of theta is equal to theta itself. You can test this on your calculator. You can do like the sine of 1 degree, get a number, the sine of 2 degrees, get a number, and it's almost equivalent to the radians that you'd find for those values. So like for very tiny angles, that holds. And so we can actually say that if we rearrange, this is what we call a differential equation, where we have something that's an acceleration, then something that's linear with a constant in front of it is equal to 0. You can see here the official small angle theorem is if the angle is small, the radian value for that angle and the sine of that angle in degrees will be almost identical. And so again, that is that relationship, and that is why we'll be able to come up with our equation for the period of a simple pendulum that we're about to generate. Now, just like the mass spring system, our solution is going to be what we call a first order linear differential equation, and that's a mouthful. But basically, when we do some calculus to this, we're going to end up with something that's a sine or cosine function. And the omega is going to end up being the square root of g over L. And so combining the fact that the angular velocity of this pendulum can be found using the square root of the acceleration due to gravity over the length of the pendulum string. And we also can find angular velocity by doing the total displacement 2 pi for one cycle when we have a sine or cosine function, divided by the time, the period it takes to make that cycle happen. We can combine these together and we end up with the equation that the period of a simple pendulum, of any simple pendulum, will be 2 pi times the square root of the length of the string over g, the acceleration due to gravity. So again, this is our period of a simple pendulum. This is given on the AP exam. You do not need to memorize it. And this is what we're going to use in learning activity number 2. We're going to verify this relationship and make sure that only the length of the string and the acceleration due to gravity impact the period of a pendulum.